right, so we're going to go ahead and get started at this time. Unit 5, Part 1, Introduction to Energy Changes. So let me get your full attention. I'm recording the lesson as of right now. So good afternoon, everyone. Just real quick, I do have your Unit 4 exams. They were not as good as I hoped, to be honest. There were some issues with functional group memorization, and there were some issues with giving carbon more than 4 bonds, actually. A little bit of disappointments there. If you see that I wrote on your test, you broke the law. You'll know what I meant. But other than that, the whole reason of making sure to give you the test before break was, first of all, I don't want to put two tests right up against each other. That's kind of difficult. And second, I wanted to make sure that you kind of got those big ideas down, because if you don't, they're really going to hurt you in organic part 2. So if I wrote notes on your test, please read over them and study it for the quarterly exam, because organic part 1 can show up on the quarterly exam. It probably won't be a large part, to be honest, because most of organic is in organic part 2, actually. Organic part 2 is the heftier part. That is, you asked how many lessons this was. This unit is 5 lessons. Organic part 2 is 9. And so that one is, because remember we took 1 or 2 of the lessons out from organic part 1 and put it in organic part 2. So organic part 2 is very heavy. It's a lot of memorization. Mentally prepare yourself for that. No, you'll be fine. We'll get there. We'll get there. Unit 5, Part 1, Introduction to Energy Changes. What is this unit then? This one's going to be short. January, it always comes up on me how short January really is. We're already a third through the month almost. I see this class 1 time next week. By the way, if that influences your choice. You see the class 1 time next week. So January is almost over, like after next week. And so we'll be in this unit just in the month of January pretty much. And this unit is an introduction to physical chemistry. Whether or not you took pre-ACE or not, most of this should be new. You may have seen some of this in physical science. Maybe, maybe not. But I know that I don't really teach energy changes much in pre-ACE, so most of this will be new information. We will be coming back to ideas about how to change moles into grams. Ideal gas law is going to show up in an example today. So have your calculators out and ready. We can also use that review, because remember, moles will be on your quarterly. So here we go. Introduction to energy changes. Let's take a look at our objectives. They're actually pretty short. There's math involved. The first objective is understand chemical reactions are accompanied by enthalpy changes, and these changes can be exothermic or endothermic. Have you heard either of those 2 words before? Exothermic or endothermic? Exo, endo. Underline them.
Exothermic. Because those prefixes, exo, outside, endo, inside.
That is a thing.
Hot temperature,
You can actually put that together.
I don't know what the big one is.
Exothermic, at its most basic, is heat excess, right? Therm, like thermometer. Heat exit. So whatever chemical reaction you have, energy is being emitted. Energy goes out from the reaction mixture. You feel it heat up. That's what we call a exothermic reaction. Endothermic means heat into mixture. And yes, it would actually mean that you feel it get colder, because it goes into the mixture taken from the outside. So these terms,
One generates heat and another one takes heat.
yep, like this, and this is like that, right? Heat out, heat in. So we're going to be looking at the concept of energy changes But we're also going to be looking at the math. There's two formulas, and I memorized this one a little bit differently. I don't like the way that it's presented. You'll see why. But I have to double check the syllabus. Q is M times C times delta T. You should write down where Q equals heat in joules. And delta H. Delta. What's that? Delta H is M times C times delta T divided by little n. I would write down these formulas. We'll be heading back to these in a little bit. Delta H is a new term. It is called enthalpy. We're going to learn exactly what that is in a little bit. But write this down for now, just to have an intro. We'll be going over each of these variables, what exactly they mean, what does that triangle mean. Not really sure I've talked about it before. Have you seen the triangle in math? Have you seen a triangle in math? No? Never saw it? In math? It means change it. Like, have you done calculus yet? Because delta y over delta x.
Oh, they got a D. It's dy.
Dy over dx.
Yeah, that's what they do. I'm just putting the book at it. That's the same thing, right?
Y2 minus y1 equals x2 minus x1. Yeah.
That's the formula for slope.
I'm just saying, in math, it shows up. It's a thing. You saw it in 1105, probably. In minor D?
Let's see.
It's going to be a constant that we're going to see later. We'll talk about it. Anyway, so 2 objectives. I know that sounds scary. That's because there's math, and we have to review math. So that's why there's 2 objectives today. Not only that, but we're still going to be on this objective on Wednesday. Why? Because we're going to do a lab that directly integrates this formula. So we will have a lab on Wednesday directly on this topic. Remember, when we do labs, they're always directly integrated with whatever we're learning. And they're also paper 3s, practice paper 3s. So it'll be a practice paper 3 from a prior year. So let's go ahead and get started. Some intro material just to go over some things you need to know. And then we'll get to the math. Like I said, have a calculator out. You will need one today. First thing. When we have a chemical reaction, there is almost always, if not always, some energy change that takes place. Before this time, we never really discussed that, but there's been many times where we've done reactions and you see it get hotter, or you feel the beaker, it gets hotter, it's steaming, or like it gets colder. And so when you have a chemical reaction, there's also some kind of amount of energy. The amount of energy we're going to be looking at energy and heat, but there are other forms of energy, like light, like electricity, electrical energy, but we'll be looking at heat in this class. So, exothermic reactions, we release heat to the surroundings. Reactions that release energy to the surroundings are exothermic. What do we mean by surroundings? Whatever's not the reaction, actually. And endothermic reaction, for that reaction to be endothermic, the reaction has to actually take in heat from the surroundings themselves. So it's taking heat from whatever is out. So some things you gotta know. Enthalpy, the letter for enthalpy is H. So you should write that. Enthalpy, some people use synonymously with energy actually, and at this level of basic chemistry, you can think of them as the same. They're not actually exactly the same, and any physical chemist would like be very mad if you said they were the same thing. But for all intents and purposes, enthalpy is equivalent in this course to energy, but it's actually constant pressure energy. And so if you were to study deeper into the class, there's actually something called E versus H. E is internal energy, H is enthalpy. Those two are a little different, whether you're at constant pressure or at constant volume conditions. And so enthalpy is actually energy, but it's at constant pressure conditions, meaning we don't change the pressure at all. We don't care because we're not looking at that in this class. So, like I said, for the most part, you're going to be able to use these terms synonymously here. But like I said, if you were to study more in depth, a physical chemist would tell you they are not the same because there's actually two different forms of energy, one at constant pressure and one at constant volume, actually. They have two different names. Enthalpy is one, the other one's called internal energy. And so, for now, this is what we're going to know. And it's H, and I am going to write the constant pressure there just to be aware of its existence, but this is not something you need to know for ACE. Like, that's not an ACE thing you have to know. Just H is enthalpy whenever we see H. So then what does delta mean? What does delta mean? It actually means something important. Go ahead, Justin. It means change in. So when you see delta in front of anything, it means change in that thing. And so there was actually a formula we wrote down that said delta T in that formula. T stands for temperature. So delta T means change in temperature, whereas delta H means change in enthalpy. So far, so good? All right, so delta means change, H means enthalpy, and then these are units. KJ, that's actually kind of a new unit. We're going to talk about that in a little bit. KJ is kilojoules, and MOLE is your favorite, moles. So units of energy you got to be aware of. First of all, the difference between joules and calories. I was very comfortable with calories, but I can't assume everybody is, because I studied nutrition before I studied chemistry, so like that was like my thing, like being able to calculate how many calories was in different things. But what a calorie is, you're not really going to see it used very much because we use an international curriculum, not an American curriculum. But a calorie itself is defined as a specific amount of energy that can heat 1 gram of water 1 degree Celsius. So when we eat food, look at your nutrition labels. They all have published amounts of calories. So that's actually telling you how much energy, the calorie is how much energy that food produces. It's potential energy until you use it. But that's how much energy that food provides. And it's classically defined as how much energy is required to heat 1 gram of water by 1 degree Celsius. And this is the one you're going to use more of the time is joules, because that's the international unit for energy. And 1 calorie is equivalent to 4.14 joules. It's unlikely. However, the 4.18 number will be important later on. So, enthalpy is defined in a chemical reaction as when there is a change in a chemical reaction from reactants to products, how much energy is released by 1 mole of a substance. So this is 1, and this is some kind of number. So you may want to fill that in. There's a number on the top, and the number on the bottom would always be 1. Unless you change it, like let's say you have 0.001 moles, then you would have number divided by 0.001 equal number over 1. But you would have to do the division, you know what I'm saying? You'll have to math that. All right, next thing. What is a system versus what is a surrounding? This terminology you need to be familiar with. It is a terminology that's used in physical science. Physical chemistry, physics uses this terminology, so you need to be familiar with it. System is literally just the molecules reacting. That's system. The system we're studying is another way to think of it. The actual reaction occurring. Surroundings is anything in the universe that's not the system. So everything else. Surroundings could be the solvent, like water. If I have my reaction molecules dissolved in water, or my substances dissolved in water, then it can be water. It could be air that's around the reaction container. It could be the actual test tube beaker itself, the outermost here. This is the surrounding to the mixture. And then anything that dips into the reaction container, like a thermometer. You put a thermometer in that, the thermometer is considered the surroundings. Are you the surroundings to the system? So there's an actual equation. System plus surroundings. You may want to write it down. It's not something you need to know for like the ACE test, not in the standards. But it's funny. System plus surroundings is defined as universe. The universe is made up of the system we're studying and everything else. This is the equation to everything. System plus surroundings equal whole entire universe. So everything else that's not the system, we call that the surroundings. And so you're going to have to be careful about what's happening to the system versus what's happening to the surroundings. You got to be very careful with this because it's going to be important. Yes.
But like, technically, I don't think the reaction is gonna involve Jupiter, you know. I mean,
Probably not going to reach that far, to be honest with you.
it's cool to think about.
But it is an interesting thing to think about, especially if you study at the A level, we get into entropy. And then entropy is like the disorder going into the universe. So yeah, it would eventually matter. But I mean, we're in a closed container of the school. So whatever we're doing here probably doesn't really exit until you open the door. All right, more info you gotta know. The next thing, and I would commit this to memory. An exothermic reaction will always have a value of the change in enthalpy of that reaction is going to be negative, meaning you're always going to get a negative number. So whenever you have an exothermic reaction where heat is being released, we describe that as a negative change in enthalpy because the system is losing energy. So what that really describes is the system is losing energy to the surroundings. You may want to write that out. System loses energy. That's why we say it's a negative sign. Negative. And so an endothermic reaction means what then? Positive enthalpy, a positive change in enthalpy, which means that system is gaining energy from the surroundings. And we can calculate exactly how much. And that's what we'll be doing shortly. Cambridge is very picky here. You must, for every calculation of enthalpy, you must include the proper sign. You cannot just give a number without a sign. You have to indicate whether the reaction is exothermic or endothermic with a positive or a negative sign. And I'll teach you how to do that in a little bit. But that's the idea. These are some example reactions of each. Combustion is an example of exothermic. Does that make sense? Combustion being exothermic. Think about what is a combustion? You burn fuel. You have a fire. What's happening? Yeah, you're releasing energy. That's the whole purpose of fuel, right? Is to provide energy. If you have fuel in your car, is to provide energy for your car to move. And so energy is being released into the surroundings as a result of that combustion. All right. Next thing, and this is something you could be tested on, so you're going to want to have an idea of what this is. This leads to something that's later on in the unit. The first way to look, before we look at actual numbers, before we look, make sure you're focusing. Before we look at actual numbers, we need to look at something called an enthalpy profile diagram. And so this is actually a much simpler version of something you see in biology. It's something you'll see later on in this unit. And what this tells you, you're going to see, and yes, there will be graphing in this unit, FYI. There will be some graphing in this unit. This is the first graph you need to understand. On the y-axis, you have enthalpy, and on the x-axis, you have progress of reaction. What does progress of reaction mean? Reaction progress. What does that mean? Goes from reactants to products. The reaction as it goes from reactants to products. And so notice what this says. You've got these reactants. This is methane and oxygen with this amount of energy. So far, so good? Reaction happens. You have, this is the wrong graph. Write that CO2. That combustion is not SH4, it makes CO2. I got it online somewhere. Change that to CO2. You make CO2 and water. Carbon dioxide and water. What are you being told about the energy of carbon dioxide and water? Has it increased or has it decreased? The energy's decreased, right? Where did the energy go? Right. So energy decreased. Energy went to the surroundings. You're being told here that exactly negative 890 kilojoules per mole of methane. And so what this indicates is that the negative sign doesn't mean that you have negative energy, to be clear. The negative sign tells us what?
That the energy decreases.
That the energy decreases for what's in the system and that it's leaving to the surroundings. You're both correct. So this loses energy as it becomes product. It loses energy to the surroundings. So would we feel hotter or colder? We feel hotter because we're the surroundings. So whatever we think is happening to us, the opposite's actually happening to the system. Kind of making sense? Okay. Yes.
In that case, can you reduce enough energy from being zero or negative?
Zero energy? There's always some energy inherently in the bonds. Yeah, in the bonds. So, no, is the quick answer. I'm going to go with no. Draw enthalpy profile diagrams for the combustion of sulfur to form sulfur dioxide. So let's see. I've seen this type of question on Cambridge exam before. I've seen it worth 2 marks. That's why I leave this in. Whenever I see a question that's like, oh, I've seen that on a Cambridge exam before, this would be worth 2 marks. 1 mark for getting your axes correct if they don't provide it. Meaning having your correct label Y and X axis. And then the 2nd mark for knowing the relative energy of your reactants to your products. So let's take a look at how we will do this. So then are we supposed to memorize our axes for this enthalpy profile diagram? And the lab, it could show up in the lab. If it doesn't show up in the lecture part, like the paper 1, paper 2, it could show up in the paper 3. So what are my axes? They're always the same.
Enthalpy, progress of reaction.
Enthalpy. Would they accept energy? Would Cambridge accept energy? They do. Cambridge accepts it. I said if you study a higher level American curriculum, they'll be like, stop that. But Cambridge would accept enthalpy or energy. And then over here, what is this?
Progress of reaction.
Progress of reaction. All right, 1 mark for that. 2nd mark. How do I know if this is exothermic or endothermic?
Combustion.
The keyword is combustion. And although you don't need to know every reaction, if it's, you know, endothermic or exothermic, combustion is definitely one Cambridge will expect that you know. Because they're like, you should recognize combustion means energy out, right? Because fuel, energy out, fire, hot, heat. Combustion means energy out. So that's the keyword that tells me that delta H is negative, and this is exothermic. All right, so this is where you have to make a decision for the second mark. Would your reactants have a higher or lower energy than your products?
Lower.
Would your reactants have a higher? The reactants are higher, and the products are lower, right? Because heat out. I still don't have the mark because I have to actually write in my reactants and products. What is my reactants here? We can do that. S8 plus O2. And my products?
4SO2.
If we balance it, without to stress it, but it would be 8, right? And this would be all right. So one mark, label. Second mark, actually knowing which one's higher than the other and filling in your reactants and your products. So this is an example of an enthalpy profile diagram. You just want to know this name. Enthalpy. They might just call it enthalpy diagram. Fill out the enthalpy diagram. You may or may not remember, it's been a minute since most of you have taken biology, but if you took biology, remember there was a curve for activation energy? Like the amount of energy needed for the reaction to take place. That's going to be coming up later on in this unit. Because all of these classes are kind of integrated to each other. All right, ready? They have to tell you this time whether it's endothermic or exothermic because like I said, they're not going to expect you for every single reaction that exists to know without doing it experimentally if it's endothermic or exothermic. So this reaction, they tell you is endothermic. Your turn, see if you can do the enthalpy profile diagram. I'll be checking it, so try it yourself. Try this one yourself. Need a pencil? Here you go. You're welcome. Ready? Remember to raise your hand and I'll stamp it. Also remember that I'm checking your notes, I believe, on the quarterly exam, if you'll recall. Your second binder check takes place with the quarterly exam. Wait on. Raise your hand when you're ready for me to check. Perfect. They have. Sorry for the pause. My brain was still. I am also still coming back from winter break. Good. Yeah. Make sure to label your active. Got it? All right. All right, I'm checking for about 30 more seconds. Then we're moving forward. Did Cambridge know that? Wait a second. Oh, I see it now. I see it now.
Good job. I'm proud of you.
I'm so grateful that Cameron people are good at reading here.
And then just put Delta H.
Yeah.
No.
Any others for me to check before I move on?
He'll just see what you were writing as an F.
No, he'll pass. Because surely they assume that I don't know all the information,
Good.
right?
No, they can't assume anything.
What if they can't read my handwriting?
I mean, they can read pretty bad handwriting, not to say yours is bad, but they can read pretty bad. I've seen, what I mean by that is I have seen handwriting worse than yours where the students have done well in their Cambridge exam. So, how do I, like, I'm trying to explain it in a way that doesn't sound, no, they should be to the side.
Okay, no.
Like, it should be progress.
They were looking for keywords. They weren't even looking for the right answer. They were looking for
Yours
keywords.
is
Probably. Okay.
All right, let's continue at this point. So, objective one is basically the terminology. Knowing exothermic versus endothermic, knowing system versus surroundings. And so, objective two, where I told you we were going to be stuck in pretty much today and with the lab next class, is measuring. What does measuring indicate? You're going to be doing that? So, in this section, we are going to explore how to experimentally measure enthalpy changes. In today's class and on Wednesday, we're going to be learning how to experimentally determine a change in energy through a chemical reaction. So we'll be seeing it in theory today, like doing the math, but then we'll be practicing next class with the lab to see it in action. The technique we're going to be used, which I don't know why we don't just use a calorie instead of joules. Like, I don't know why we use joules when we call the technique, and Cambridge calls it this, calorimetry, which sounds like calorie to me. So calorimetry is the experiment that we do to measure enthalpy changes in a chemical reaction. Yes? No, they use joules. So there's like these exchanges, you can buy food from other countries, and you'll see that they're published on the back. It'll say joules instead of calories, and then you just do that quick division, divide by 4.184, and you'll find the amount of calories in that food. I always think of when somebody asks that question, I think of Mean Girls, and how Regina's like, how do you even know what's on this bar? Different countries, different units. Yes. Go ahead. She didn't know those calcium bars would make her gain so much weight. Anyway, so going back to what we were saying, measuring enthalpy means we are going to be measuring how much energy is going out or how much energy is going in. So what will we need to be able to do that? How can we do this? It is actually one of the simplest experimental setups you'll ever see. And this is why when you take your paper 3, we are not allowed to let you in the room until it's time. Because you can look at the experimental setup, and if you see exactly what I'm going to tell you, you're going to be like, oh, I don't do an enthalpy today. Like, you'll know just by looking at the setup. Here it is. You're going to have a beaker. And inside of your beaker, you're going to have a foam cup. It is a foam cup. We call that an insulated cup. It's made out of foam plastic because it doesn't let heat escape if there's a lid. So it's actually called polystyrene. It's a polymer. We'll be learning about polymers in organic part 2. But it's a foam cup, pretty much. You can buy them super cheap at Publix. I do. I buy them. 50 cups is $1.50 or something. They're super cheap. They're super bad for the environment as well. Wait, okay. Oh, what can you do? We learned about that, didn't we?
Yeah.
Plastic mean how you get rid of it. How you get rid of that.
Yeah, we concluded that the only way to get rid of it.
You You can burn them, but then you can use gases. Not great, but anyway, so we use what's called a simple calorimeter. We're going to be learning about two different types of calorimeters. I actually have both of them, but Cambridge only requires you to use one, the simple calorimeter, which is made of a foam cup. Other calorimeters that are more fancy include metal cans and flasks, but we're going to use the foam cup set. That's why I said you walk into a Cambridge exam paper 3, you see a foam cup, you're like, I know what I'm doing today. You'll see the lab on Wednesday. All of these containers should have a lid. Cambridge may or may not give you a lid if you have that on your lab exam. Why wouldn't they give you a lid? Because one of the questions you can get on a paper 3 is how can you improve this? Sure. And so the reason you would have a lid is to minimize heat. Lid minimizes heat escape, right? No.
Where do you bring your own when I know how to fix
You can't bring your own stuff. You can't bring your own stuff. You can only
it? Pull out your own lid.
failed. Brought in proper materials to the exam. You can't bring your own stuff in for the lab exam. But all of these containers should have a lid. And the reason for this is, well, if you're trying to measure the energy change of the chemical reaction, if there's no lid on, what's happening as the reaction's going on? Heat's probably escaping. And are you going to be able to measure it if it's gone into the air? No. You have to capture it in the system, right? So you have to try to capture it in the container as best you can. And so the more heat that you lose to the surroundings, the more inaccurate you're reading. So could you see like a percent error question here?
Yes.
You could totally see another percent error question here. So the more heat that you lose to the surroundings, the more inaccurate the reading. I'll be looking at what lab to choose for you tonight. I'm just giving you ideas of what you could be looking at on Wednesday. You're going to see a foam cup. You're going to see some reaction mixture. So you're going to mix things together, right? Mix things together, do reaction. I haven't chosen the lab yet, so I'm not telling you if you're getting a lid or not. You'll be missing your lid. Possibly. And what else is here? Thermometer. So what is the actual measurement you'll be taking? The temperature, right? You'll be taking the temperature. This is to read the temperature. As a result of the reaction occurring, the temperature may go up or it may go down. It'll go up if it's exothermic. So what you're going to see is that in the thermometer, the temperature goes up if it's exothermic, and the temperature goes down if it's endothermic. How's that possible?
Heat.
Is the thermometer itself a system or a surrounding? So if heat is leaving, it's causing the temperature in the thermometer to go up. If heat is entering the actual reaction, it's actually stealing energy from the outside, right? So the outside gets colder as the reaction itself gets hotter. And the thermometer is part of the surroundings, not the system. So that's why you gotta be careful here. You should write this down. If the temperature goes up, you have something exothermic, which means your delta H will be negative. And if the temperature goes down, this is endothermic, which means your delta H will be positive. Yes? Okay, so this is the lab. This is the lab you're going to see on Wednesday. But we got to do the math. What's the calculations look like? How do we figure out how much heat is released or absorbed in a chemical reaction? That is the Goldilocks way? Well, that is not very accurate. So this is the equation. You do need to memorize this formula. It could be on your quarterly. Remember I told you that anything that shows up today can be on your quarterly. So add it to your PV equals nRT and all your other equations you need to know. Yeah, you gotta go back and review them. Q equals M times C times delta T. What does Q stand for? Let's go over what each of these things stand for. Q is energy transfer. The unit we're going to use is joules. M is mass, specifically of your water or solution. You should write or solution here. Because it's either going to be water or it's going to be something that's dissolved in water. The unit for mass is going to be grams. C is called heat capacity, specific heat capacity. And this is a constant. It is 4.184 joules, grams, times degree Celsius. Believe it or not, this constant is given on that little sheet that they give you with paper 1 and paper 2. They're not going to ask you to memorize this constant. However, you may memorize it just when you're doing practice questions. This is the constant. Once again, calorie would make more sense. It's hilarious because the constant for water for calorie, guess what number it is? If we were using calories instead of joules, we're required to use joules. 1. C is 1 if we're using calories. But we use joules, so is this?
Just the
So we just be 1 if we use calories.
we do have better.
Okay, that's it. That's pretty
Okay.
much it.
This specific topic, maybe. But they make other things easier, so can't complain. All right, delta T. Change in temperature. There are 2 ways you can think about this. I'm going to tell you both, and you can make a decision of what you want to do. Officially, the formula for change in temperature is delta T equals the final temperature minus the initial temperature. So technically, delta T is TF minus TI. Final temperature minus initial temperature. If you follow this formula, it will actually give you the correct sign for enthalpy. If you follow the formula they give you in the front page. But I actually suggest just recognizing change in temperature just means bigger number minus smaller number and not getting confused with the signs. And then knowing that if it's an exothermic reaction, you write a negative. And if it's an endothermic reaction, you write a positive. So there's 2 different ways to go about it. My suggestion is to do bigger number minus smaller number, and then you always have a positive. And then just know if it's endothermic or exothermic to choose your sign. The reason why I suggest that is if you use this formula, you'll have double negatives going on at some point, and you may get confused. But delta T just means change in temperature. Unit is in Celsius, so you should do this in Celsius. But it actually, as long as you use Celsius or Kelvin, it technically doesn't matter because it's a change. And so, because it's a change, it doesn't really matter. How do the units work out? We said mass is in grams. C is in joules per gram times degrees Celsius. And delta T is in Celsius. So, how do the units work out for this formula?
Just GGA.
Which is what I told you. So if you use the units the way that they're presented to you, you'll always get the answer in joules. It should always be in joules. Your answer for Q will always be in joules. Q is in joules when you calculate it. There's a couple of things to be aware of. This is going to be important, especially for your labs, for some of the homework, but especially for your lab next class. So you must know the following assumptions. And why am I going to call this an assumption? Because if you have a dilute solution, what does dilute mean? You can use this assumption. Okay. First thing, in all of the math questions you're going to be given, you have to assume that you have dilute solution. It turns out that 1 centimeter cubed is the same thing as 1 milliliter. We hopefully remember that. In America, we read milliliters. In international, we read centimeters cubed. The way we report our answers is in centimeters cubed. But do you remember that the density of water, and this is something that I taught, I think, in pre-A, is 1 gram per 1 milliliter. If you don't write it down, this is super important. The density of water is 1 gram per 1 milliliter. So when I read milliliters, I pour out water, and I pour out the milliliters. That's also the amount of grams. So this means that if I measure 25 milliliters of water, the mass is also 25 grams. You should write this down because it's going to show up in your lab. They're going to ask you to measure a volume of water or a volume of a dilute solution, and you're going to have to know to use that as your mass because of this. The density of water and for dilute solutions, meaning lots of water in the solution, is 1 gram per 1 milliliter. Why does that matter? When you go to this formula, this is going to be the mass of water that you're measuring. It's really important you have this written down. Like I said, when you get to the lab, this is going to be something that ends up confusing people, so I'm going to. It's also going to show up in the homework. Got those calculators out? We're about to get to the math.
Oh.
Got that formula. Don't you see the next one? Check up 4. It's math. Ready? Yes. Yes. All right, I'm giving you about 20 more seconds, then I'm moving forward. Yes. Yeah, and it's not grams. Because they're 1 equals 1 equals 1. That's why. So they're all the same. They could be interchanged. For what?
Why don't I run I thought the Q you wrote was 2.
Oh, my bad. That's a okay, let's get to it. Starting with level 1, because you know how it goes. We always got to start with easy examples and then step it up. So starting with the easiest it could possibly be. Check up 4 from the textbook. Calculate the energy transfer in kilojoules with a temperature of 75 centimeters cubed of water rises from 23 degrees Celsius to 54 degrees Celsius. Remember that the constant that we're going to be using is 4.184. Is this provided on the little sheet of constants? Yes. Will I remember to give that to you on the quarterly exam? I hope so. Yes. say it out loud so I remind myself. Here, give this. So, what do we do? How do we do this? Where do we start? What do you think?
Change from centimeters cubed to grams.
Start with our formula, right? So,
75.
M times C times delta T. All right, let's start with mass. M stands for mass of water or mass of solution, whichever one we're working with. Here we're working with water. So what is the mass of water here?
75.
75. Because the idea in your head you've got to remember is that these are the same. Whatever the centimeters cubed they give you, that is the grams for water. Because of this. So, 75 grams. Are we good with that? You got to do that in your head. Just make that switch. All right. Next, C, 4.184. Next, delta T. How do we want to do this?
54 minus 20, 31.
31. Yes.
And 727.8.
I will do my calculator very shortly. Probably. It sounds in the right range. You did 75 times 4.184 times 31. And this tells you the amount of energy transferred. If you need a calculator, don't forget I have some you can borrow. I keep them up at that table if you need a calculator. I got 9727.8, so that's correct. Let's talk significant figures. Where shall we round?
The three significant of the most important values. 2,728.
What is acceptable for Cambridge? 3 or 4. So it looks like we can round the whole number to 4, right? So let's do that. 97, 28. What is the units? Question for you. This is correct. But what if you needed to change joules to kilojoules? Because you will be asked that.
But doesn't it ask for kilojoules?
Does it?
Yeah.
Oh, yeah. So we got to do it here. What if you need to change to kilojoules, which apparently we need to do? That's one way you could do it. There's multiple pathways. Either divide by 1,000 or move your decimal place over
9.72.
3 spots to the left to go to kilo, right? So it would be 9.728 kilojoules. And so that will be our final answer. Be careful where you could get messed up here is in the units. Make sure you are carefully identifying what units being asked for. Yes. Because that's the actual, if I fill out everything, that would be it. Like, it would be 75 grams times 4.184 joules, grams times degrees Celsius times 31 degrees Celsius. If I plug in everything, that's what I would plug in. You don't have to do that though. You don't have to write the units as long as you know it ends up being joules. This is to prove that it ends up being joules.
So C is equal to 4.1.
Yeah, that's a constant. Those are the actual units, and that helps you to understand that these all cancel and you end up with joules. But you don't have to write that in. And that's actually in the formula sheet. Like, all of that information is in the formula sheet. But all you have to do is plug in the numbers here. Good? Plug in numbers, make sure your units are correct. Next one.
254.
Check up 4B. Let's be careful here.
It's also kilojoules, so you can move the decimal point 3 times to the left, and that just looks wrong. So then it's 0.2 2,
Welcome
5,
back.
4, 1, 7.
So, stepping it up one little notch. What's the formula again? Go ahead. Q equals M times C times
Delta.
delta T. Okay, be careful. There's more than one mass here. Which is the correct mass to use?
Water? We use 1 more. I just added
40 centimeters cubed.
because it's a solution, so they're together.
Yeah, well, that's what I did.
That's what I did.
Oh, but you did mention that we're supposed to use the field mass, right?
Use the mass of water.
Only one? Okay.
Yeah.
Whoops.
If it's sufficiently dilute, use just the mass of the water. So the other mass, you'll see where we're going to use it in a later question, but not here actually. You want to use the mass of water because that's what you're measuring the temperature of, and this is interesting. When you think about it in the lab, it would make more sense. You take the temperature of water before you put the sodium chloride in it and after, so it doesn't change much. And because it doesn't change much, you just use that amount. Yes.
Negative 5.04.
It's not negative. But I'm gonna explain. I think I know how you came up with negative.
It says that it's in our boss.
Yeah, but it says how much energy is absorbed. You can't have a negative amount of energy absorbed if energy is absorbed. It's not asking for delta H is the issue.
But then, yeah, and then you
Without-
it's like a 2,
Yeah.
2, 5, 1.
All right, so let's take a look. Mass is 40. D is 4.184. Change in temperature. My suggestion is to do bigger number minus smaller number. 1.5. And so this will give you an energy transfer of. Do they tell you what unit they want?
Yes, littles down there too.
How dare. Not how dare you, how dare they. 151 and then 0.2. Change it to KJ, right? A little bit small. But when you change it to joules, you're like, man, that's big. And if you were like millijoules, you'd be like, that's really big. Even though they're all the same amount. I have a fun fact for you. Do I have time for it? But
There's always.
if you eat a cheeseburger, the calories on your label are not calories on your nutrition label. They're actually kilocalories. So when you eat a cheeseburger from McDonald's, let's say you have one, and let's say it's 300 calories. Capital C actually means it's kilocalories. So it's actually 300 kilocalories. How many calories does that mean your actual cheeseburger is? It's actually 300,000 of the little calories. So which means
Insane.
you could heat 300,000 grams of water by 1 degree Celsius with your one cheeseburger.
Well, that's not.
So by definition,
Don't have a cheeseburger.
no, it means we must require a lot of energy to live, right? We need more than one cheeseburger worth of energy a day. You need like 5.
Nuggets.
Yes, most people need at least, like if we talk about it in cheeseburgers, you need like 5 to 7 cheeseburgers a day. If you just eat cheeseburgers and nothing else.
That sounds terrible.
In micronutrients, but I'm just talking about calories. Anyway, that was your random fun fact of the day from Miss Lee. All right, let's continue. Of course, I'm just talking about calories. I'm not talking about micronutrients. A cheeseburger is not a healthy diet. But let's continue.
I mean,
4C. Step it up again. What do we got going on here? A student ads.
Oh, no.
This is actually probably similar to the lab you'll do on Wednesday. I'll be looking for something similar to this. A student adds 50 centimeters cubed of sodium hydroxide and 50 centimeters cubed of hydrochloric acid. They basically just go, boom, mix them together. Both solutions should be writing Q. They're different. I'm going to explain to you exactly why they're different very shortly. We've only been calculating Q so far. Welcome back. Yeah. Just, I'm going to remind myself of saying it out loud. I need to give you back your test. If that's okay. All right. So Q equals M times C times delta T. What is our mass here?
Mass is a number between.
I'll say 50.
Yeah, just take half of each.
So think about what you're actually doing. You got 50 centimeters cubed of NaOH. You got 50 centimeters cubed of HCl. And you're putting them together in a beaker. What's the volume?
100.
So you mix them together.
Yeah.
So what's the mass?
100.
100.
Oh, it's just all of it?
Then why couldn't we add it?
Million, yeah.
Because it's very small amounts.
Oh.
These are equal amounts, like 50 and 50 will change your mass volume. Neutralization, you just add the volume.
Okay.
So add volume. That's a significant difference. Whereas 14.5 is not a significant difference, that's why it's 1.5. C. What's the number for C?
4.184.
And the T.
33 minus 18.
Oh, no, so it's 850.
So what is this?
A number.
6.276 kg.
5276 joules. What are they asking for? Energy. It doesn't say a unit. So, question. If Cambridge doesn't ask you for a specific unit, is this good enough?
Yes.
Yes.
What if I did like it, like
95 kilojoules.
It would be okay too. So that's, there's,
calories?
We
just
can.
like that.
Yeah.
they don't specify a unit. If you want to divide by 4.184 and change the calories.
That
Yeah,
sounds so
great.
risky for no reason.
Going to do it.
Risky for no reason, but whatever.
Out of spite.
Have fun.
Lose your points for no reason.
All right, ready to continue?
No.
Step it up. Uh-oh. Let's take a look at this.
What are pastels here?
Miss, I think it's
Oh,
a
no,
bit
hate that
too
guy.
large.
Can you read it?
I think it's a bit too large.
All right, I'll read it out. You've got 125 centimeter cube sample of propane. Measured at 20 degrees Celsius and 101 kilopascals, burnt in air. So you've got some propane gas. I'm going to write it down. 125 centimeters cubed. You've got 20 degrees Celsius, and you've got 101 kPa. The heat produced raises the temperature of 200 grams of water by 13.8 degrees Celsius. Assume no heat is lost to the surroundings during this experiment. So that's the assumption you're making, that you could basically use these formulas, that's the amount of heat that's transferred. First question. I told you we gotta review it, right? This could be on your course. Use the equation PV equals nRT to calculate the mass of propane. So, do you remember this equation?
Yeah. P is pressure, V is volume, N is mass, R is constant, and T is temperature.
Okay, so for propane, we have centimeters cubed. What is that unit?
Volume.
Volume. Is it in the correct unit?
No, it has to be PM2.
It actually has to be
Yes.
meters cubed. For PV equals nRT, volume is meters cubed.
So close, no matter how far. 6 units to the left.
So 3 zeros. Unit change. All right, next thing, temperature. What is the unit of temperature? Kelvin.
The added, like,
What you gotta add?
270.
Oh, there's a three.
Yeah, 273. So this is stuff you may need to add into your, I need to review this for the quarterly.
Kilopascals.
You turn it into
Oh, I forgot to say, if you chose the quarterly for Wednesday, we'll do a quarterly review on Tuesday's tutoring next week, the day before, which is looking like, last time I looked, that's what it looks like it's gonna be. 101 kilopascals, change that to Pascal, move it to the right 3 spots, or multiply by 1,000
So it's 101,000.
Pascals. Okay,
Plug it in.
so plug and play. Pressure is 101,000. Volume is 0.000125. N, we don't plug it in anything for that because that's moles, and that's gonna get us to grams. Yes, 8.31 is correct for R.
I was so smart.
8.31? Oh, that's the gas constant. It's also on that
Little
paper.
paper, we don't have to remember.
You don't have to memorize it, but you just do. All right, now read it carefully. Temperature would be 293. All right, solve for N. I'm gonna get my paper up because I already did this. Solve for N.
This is by far the easiest part of the class.
Committing internal work on it.
See if you get what I got. 0.00518 per mole. If you don't get that, let me know. I solved for moles. Make sure you're writing it down. I get 0.00518. Check to see if you get the same. Time for you to see. Plug it in your calculator, do your multiplication and division. See if you get the same answer.
What? I got 5.18.
Why did you move it over?
I have 100 times 0.00125
What was the conversion?
divided by 8.1
Celsius plus 350.
divided by 33.
You right, but also I got this.
I got
I didn't write much.
You got the same thing.
Yeah.
5.19 times 10 to the negative 3.
Oh, -3. It's my calculator. See, the calculator always gets me.
It's 0.00519.
Yeah.
Oh. That is right. You have it.
You're so smart.
Are you good? You good? You good?
What?
Okay.
What's the speed represent?
All right. So
Pressure.
let's take a look at the next question. How many marks do you think this is worth? Part 1.
4.
Most likely 2.
Numbers.
Most likely 2 for that first part.
It's not too hard, but like.
Let's try part 2. Use relevant data from the data booklet, so you can tell this is an older question prior to 2022. You would actually be using the little chart that they gave you with the constants, that's what they're telling you, to calculate the amount of heat released. So underline amount of heat released. What are we looking for? Heat is Q. So remember, heat is Q,
Oh, that's something we learned today.
and enthalpy is delta H. You're going to want to write that down. Heat is Q, enthalpy is delta H. You're being asked for Q. So what's the formula for that?
U equals
M
C delta T.
Alright. Where's the information for that? Do you see it?
Yes.
It's in this sentence right here. I'll write it out. It says the heat produced raised the temperature of 200 grams of water by 13.8 degrees. So for water, we've got 200 grams.
Is temperature also in Kelvin? Or do you use the one they give you, like Celsius? It has to, because the number will be different.
It technically doesn't because it's a subtraction either way. It's a change in temperature. But it's, Celsius is fine. Celsius is right. All right. What's our mass now?
Something.
200. The grams of water. Why don't we add, pay attention to this, why don't we add propane gas to that? Well, first of all, it's a gas. So it's not in the water, right? And, well, that is the reason, it's a gas, and it's actually not inside of the water. You'll see when we do the next slide why that's so. It's actually not part of the water. The gas is somewhere else. The water is measuring the gas in a different place. All right. C is what? Four. Some people round differently. Like sometimes on paper 3, they'll tell you it's 4.18 or 4.2. Just use whatever number they give you. It is 4.18 for 4 significant figures. And delta T is what?
6.2.
No. What is delta T?
6.2.
13.8.
13.8. So you have to read it carefully. It raised the temperature by 13.8. It didn't say the temperature went from 20 to 13.8. Be careful. By means this is the
I
change.
also got it wrong. I put 6.2.
All right, so 200 times 4.18 times 200 times 13.8. What do we get from this?
11,540.
I get 11,548 joules. What would that be in kilojoules? I like kilojoules better.
11.
And I'm going to do 3 significant figures because too many numbers. 11.5 kilojoules. Did it have to be in kilojoules or could you have left it in joules?
I could have left it.
You can leave it in joules. Next. Last question. If it's rounding,
Oh,
you
it's
can
because
trust
it's
it.
0.4. Never mind.
Use the data above and your answers to 1 and 2 to calculate the energy produced burning 1 mole of propane. So pay careful attention. This is something new. We have the energy that was used to burn how much propane?
125.
How many moles of propane specifically? They said use your answers to 1 and 2 to calculate the energy produced
Oh.
by burning 1 mole.
It's 5.1.
Don't we have that here?
Yeah.
We know that 11.5 kilojoules is the amount of energy for 0.00519 moles of propane. How do we figure out the amount of energy for 1 mole of propane? What could you do? Anybody have a suggestion?
Divide 1 by 0.05, 0.00519,
I like your train of thought.
and then multiply that by 11.5.
It would work. Get your answer, and I'm going to show an alternative way. But get your answer and make sure they match. Here's what I would do. You want the kilojoules per mole, right? That's what they're asking for. Do you have an amount of kilojoules? Do you have an amount of moles? Divide them. the number on the bottom will change to 1. Do 11.5 divided by 0.0051. And you should get 2,220. Kilojoules per mole.
Makes sense.
Is it fun?
You will say
Kilojoules per mole. All you do is you take this answer and divide by this answer.
Oh, wait, it's down.
Let me check yours. Yeah, it's rounded. Yeah, I got the same thing as you. Just round it to the correct amount of significant figures. All right. That was how many marks in total? What's the number at the bottom?
only 5.
That was 5 marks for all that math.
Well, the first 2 were 2 points, and then the last one was 1.
Yeah. All right. Let's take a look at this in paper 1. Ready to look at paper 1? Okay. Before I continue, as we look through this question, let's talk a little bit more about Q versus enthalpy. We said Q was heat, and the unit was joules or kilojoules. So then what is enthalpy? I had mentioned it right at the beginning. It's actually the kilojoules per mole. And it's the change in kilojoules over the moles. So remember that enthalpy must be given a sign. You either have to say that it's negative or it's positive. We haven't actually done that yet because we were only looking at Q. But once you're being asked for enthalpy, you actually have to say whether it's endothermic or if it's exothermic. We're going to say it's endothermic with a positive sign, and if it's exothermic, it's with a negative sign. So let's take a look at the question. Paper 1. Student mixes 25 centimeters cubed of 4 molarity hydrochloric acid with the same amount of sodium hydroxide. The initial temperature of the solutions is 15. The maximum temperature is 30. Using these results, what is the enthalpy change of neutralization of hydrochloric acid? So let's start looking at what are we being asked for? Enthalpy change. Which means, am I looking for Q or am I looking for delta H? Before I can find delta H, I first have to find Q. Because remember, delta H is actually the kilojoules per mole. So when you were asked for this thing right here, they're technically asking for the enthalpy without saying they're asking for the enthalpy. All right, so let's find Q. How do we find Q?
M times C.
You think you should memorize that formula?
Maybe.
Well, you need it for the lab on Wednesday. So, what is my mass? Read the first sentence carefully.
It's 40. 80.
What?
Huh?
I was just saying random numbers. It's 50 because it's equal to volumes of something. 25 is 5.
So you have basically 25 centimeters cubed of NaOH being mixed with 25 centimeters cubed of HCl, 50 centimeters cubed of mixture. Yes?
Yep.
So mass is 50. C is 4.18. Delta T is 15. All right, what we got for Q so far? I got, when I did it, 3135 joules. Check to see if you get the same thing or something very close.
138.
I did, yeah, 3138 is good. 3138 joules. Joules. Notice,
Good afternoon, teachers and students. One announcement. Student ambassadors, please report to room 30 at this time. Please bring your books. Student ambassadors, please report to room 30 at this time. Thank you.
in order to get enthalpy, we first needed to get Q. But the units of enthalpy are kilojoules per mole. So we've got joules. How do we change that to kilojoules? So we know that we got to move this over. And that's going to get us to 3.138 kilojoules. At this point, notice how two of the answers are there. One of them looks like it's that answer, but it's not. What do we still have to do? We have to take this and divide by moles. Wait. Moles of what, first of all?
Of hydrochloric acid.
Because it said hydrochloric acid, right? So we need the moles of HCl. Do I have information in the question to get the moles of HCl? I do. What do I have to use to find it? Concentration equals moles over decimeters cubed. Concentration is 4. Moles is what I'm looking for. And what's the decimeters cubed?
Centimeters, so then you move it over 6 to the left.
3.
Oh, 3.
Because centimeters to decimeters, 0.025. Solve for moles. What do you multiply both sides by? So is that stuff coming back?
Yes.
Yes, it is. 0.025 times 4 is what number?
0.1.
0.1. So now what do? We got the moles. We want the enthalpy, kilojoules per mole. Now what? To find delta H, we write 3.138 kilojoules and we divide that by 0.1 moles. So what is that answer? It is going to be B. So it's 31.38 kilojoules per mole. Why is B the answer? Well, be careful. There's something different about B than what we've currently written as an answer. Why is B correct? It is. You're missing something very big. We have to give a sign, whether it's positive or negative. So this negative is communicating that it is exothermic. How do we know that this is exothermic? Where does it say that? Yeah, thermometer temp goes up, equal heat release. So that's what tells us it,
I mean, but they all have the negative.
because you got lucky. Couldn't there be another question where they put positive 31.4
same
and
answer
negative
twice,
joules?
and you get plus one and
Yes.
negative one.
Yes,
I thought you.
that's how it should be. So make sure you're paying careful attention. All right, we're almost done. I'm just gonna bring up one more thing before we go. Remember that question I told you, the propane gas could not mix with the water? That's because this is the other type of calorimeter. You're not gonna have to memorize this setup, but I wanna bring up, you can use a metal can if you have to burn an organic fuel. And what happens here is the heat from the burning transfers into a vat of water. So this water is what you measure the temperature change of. You will not see a lab like this on your paper 3. However, you could get questions about it. So all this means is that if you have an organic fuel, yes, there's a stirrer. You would measure the mass of the water you would measure the change in temperature of the water. You would not add in the fuel to the water because the fuel you'll see is in a separate container from the water. So this happens whenever you have organic volatile fuels. This type of calorimetry is actually what they use for measuring the heat of foods, like how much heat food provides. They basically burn it, see how much the change in water is, and it tells you how many calories your food has. That's what they do, is they use this. We're almost done. This is a repeat of what I said before. You have to give the sign for enthalpy. And so, as we do our last question, this is where we'll continue next class, actually. Let me double check the homework. You should be able to do the homework, but I'm gonna give you a little bit of extra time. You'll have till Wednesday night to do the homework, just so that we do a couple of examples together next class. And you'll have the lab next class, of course. But I'm passing it out now. I also remember I'm gonna pass out your test so that you get that back now to look over. Yes.
Is there a tutorial tomorrow then?
Here's tutoring tomorrow. Yes. Homework help and review. The review for the quarterly will be next Tuesday because by overwhelming votes, the vote was for next Wednesday for the quarterly. 14 to 4. Yeah. Online. Online. Go. I'll be giving back the test after I give up the homework. And welcome back. Back to this.
Yeah.
Lab next time.
Also, didn't tell me it was your birthday. I heard something about war.
Yes. What do you need?
Don't understand.
Hold on, one more time.
Did you know that the I can't think long enough for the story.
Yeah, I think I have those at home. I'll try to get this ready for Wednesday. I have the uniform. I think I put them in a drawer at home. I don't know why I brought them home, but I think I brought them home. I'll check when I get home.
I don't know.
All right, so I have the tests. I'm shuffling them. They're handed out in no specific order. Alina? Yes.
You should erase that. You just have it memorized. That's crazy. Give 5 cents.
Make sure to read the notes and start it over and make sure you understand it before the quarterly meeting. David?
I don't know so much.
Thank you.
Diane?
How do you know so much?
Alex?
Do you follow the river Styx?
Mariani?
Your nose feel like you're like an English man.
Ernesto? Matt? Can you divide it for here? What? Yes, it's in the back, yes. No distraction. Bye. See you tomorrow morning.
I believe in you. I believe in you.
All right, so the vote. Let me just double check with one more check. So with a split of 13-4, you're taking the test next Wednesday. And it has to be done by Thursday because you're ending the quarter. So you're taking it on Wednesday. Everybody takes the test next Wednesday. You can drop
I
it.
got confused. I got sick. Like completely. I switched up. Did you remember what No, I put standard and displayed and displayed and standard. And I changed it like 3 times, so I wasn't sure.
I don't know if I have that again. All right, let's go over your test. You know what you
I
got study.
completely got an entire page.
You got right, you got wrong.
Even my
Not displayed. Not stated. That's so stupid. I could have got it already.
I'm gonna cover activation energy later in the year. Oh,
You didn't take it.
After we do
I don't know
empathy,
how much I'm charged, but higher than class. It's still a 0.
Mine is.
All of you at the same time.
That's true of you. Yes.
Okay, it doesn't matter who it is. I already know what you're doing. It doesn't matter who it is. It's your fault. I'm closing my eyes. I'm not there. I'm not there. I'm anywhere else but there. I'm gonna leave. She's not gonna hear from me ever again. Ever again. Ever again.
all right, don't forget regular tutoring tomorrow. Lab on Wednesday.
Oh, then she knew what was coming. Okay, she knew what was coming.
Ignore them, they are.
Tutoring tomorrow. Regular tutoring tomorrow. Test review next week. Just practice questions. The rest of the quarter. That will be there. I cannot yet tell you the amount. I didn't know by Wednesday.
I think I should be fine considering I got a decent grade today. I think, yeah. I'll be fine.
What are you doing? Wait, if you're leaving, I mean, you're going to 6.
Oh, the unit.
The hard
But you are trying to get it in.
I think you guys were considered. Remember that you can drop your low score if you want to. Yeah, you drop it.
But it's so much money.
If you have one bad test, you always get.
Yeah, that's what, $1 million to go with it?
If you do well,
Yeah.
you get it.
I'll be there before and I
It's based off everything. So if you learned it in the quarterly, I replace your lowest exam.
Good afternoon.
Those
You're skipping the.
you already get it.
Meeting at the campus today.
You like
Meeting
math,
this Friday.
where you have to try to do well. There's a lot of basic connections. Doctor, I'll report you.
Meet us today.
I'll see you tomorrow at your ring. You still get the 5% extra credits for your next unit exam if you come back. Bye. I'm happy to see you all back. Happy and hopefully healthy.
I want him.
Bye. Bye. See you Wednesday, Lab Wednesday.
Bye, Miss Lee.
Bye. Happy to see you all back. Hope you're happy and healthy. Oh, maybe stop by tomorrow after school. I'll see what needs to be done for the lab on Wednesday. Possibly. Tomorrow after school we have tutoring anyway. So check tomorrow. You could also for Wednesday after school after your lab. Possibly I might need help. I'll let you know tomorrow if I need help tomorrow or not, but Wednesday after school, after your lab, I'm sure use help with cleanup. Although enthalpy is not too crazy with the amount of, like you saw the setup.
Yeah.
It's pretty simple in comparison to some of the other ones. All right, bye.